Okay, let's look at domain and range part B, part 2, which is for continuous data. Let's just refresh the definitions before we start. Domain, the defined or naturally unrestricted set of values allowable for the independent variable, commonly called x, or the variable on the x-axis in an algebraic relation. Range, the defined or naturally unrestricted set of values allowable for the dependent variable, commonly y, or the variable on the y-axis in an algebraic relation. Okay, so now let's talk about continuous data. Domain, range for continuous data. Let's scroll down just a little bit here and make it easy. Okay, continuous data is data that results from an equation, and when plotted on a graph, it is continuous between defined endpoints or unrestricted except for the physical limits of the graph paper. And if that's true, normally what we do is we indicate the arrows on the lines of the equation to indicate that it keeps on going. Okay, and the other thing about continuous data is when you look at a plot of continuous data, or when you're making a continuous data plot from an equation, you can do the plot between the endpoints or to the arrows without lifting your pencil from the paper, because the word continuous means that it keeps on continuing, and there's an infinite number of data points that you could plot which would all connect. Okay, in the case of discrete, I may have failed to mention that, but discrete means individual points, individuals. The word discrete, you might want to look that up and get a good English definition of that. Okay, so let's look at some examples. First of all, let's just look at a simple line, and we'll consider that this one is unrestricted. Okay, so we'll put our, let me see if I got a blue, yeah. So what we would do is put blue, I thought I had blue there. It should be blue. I don't know why it came out green, but anyway, there it is. Blue arrows with the blue line to indicate that that graph just keeps on going. And this is what we would call unrestricted. Okay, this is a linear equation. It has a slope of let's see, down 2 over 3, so that has a slope of -1/2. Okay, so we could actually define this equation while we're doing it. And so y equals a minus, remember, downhill from left to right, down 2 over 3, so it'll be 1/3, right? X, and our y-intercept is +2, right? Okay, or 1, 2 here, 2, 4, and so forth. All right, so there's our line, and the question you would ask yourself of this line is, if my paper was large enough to keep on going as far as we could possibly see, is there any reason that this graph would not continue on in the x direction this way and in the x direction this way if we didn't place any other kind of limits? Okay, and I think what you can tell is, yes, there's no reason that this graph wouldn't continue to go in both directions. Likewise, we can look at the y direction and say, okay, as x continues to move in the negative x direction this way and in the positive direction this way, plus x, is there any reason that the graph would not also continue really ultimately to infinity in the plus y direction heading this way as the graph moves, or in the negative y direction down here as we continue to move? Okay, and so we would say that this graph is unrestricted, so the domain is going to be x is going to go negatively, but x is going to be greater than or equal to negative infinity. Whoops, not greater than or equal, it's just greater than negative infinity and less than infinity. Okay, so the domain then is x is greater than negative infinity, and so it goes all the way from negative infinity to positive infinity, unrestricted. Likewise then, the range would be y is going to be greater than negative infinity and less than infinity. Okay, and it's unrestricted also. So the domain and range, and now there's another way we could state this. In fact, I'm going to show you two more ways. And one way would be, I could say, in verbal terms, I could say that domain is all real numbers, right? Because every way I go in the negative direction in the real number system, or every way I go in the positive direction for x, is all real numbers that way, and the same thing for range in this case, okay? All real numbers, okay? Now there's a third way we could list this. So these two things mean the same thing, okay? There it is with notation where we use the greater than or equal to signs or greater than signs, and this is verbal. The third way that we could list this, which is actually a lot more convenient, and you will see this more and more as we go into Algebra 2, is what we call interval notation, okay? Interval notation, and I'm going to write it up here, but I'm going to, you should go look at the video lesson on interval notations to get the definitions exact. But the interval notation for this would be like this. It would be negative infinity to positive infinity, and the soft parentheses indicate the same thing as greater than and less than. They indicate that the endpoints are not included, okay? And so we would use the soft parentheses here for that. And you can see that's a whole lot simpler, quicker way to do the notation. I like interval notation, and the higher you go in your math, the more common that will be to use that notation. All right, let's look at a different example. Okay. Let's look at a curve like y equals the square root of x. Now, remember when we're using a square root of x with no sign indicated, like plus or minus square root, when it just says square root, we're talking about the primary square root. Primary square root is all the positive ones. So let's write that down. Primary square root of a number is the positive values. Or we should say positive value solutions, okay? If we had plus or minus, then you would go ahead and indicate that. All right, but in the real number system, and this graph is going to indicate real numbers, of course, so we got x and y. If I plot this, the square root of 0 is 0. The square root of 1 is 1. I'm going to go ahead and use the red boxes to indicate 1, 2, 3. This time 1, 2, to make it easier to plot. And so this would be 3 and 4. Okay. So the square root of 4 is 2. So I would have this out here. This would be it. At x equals 4, then y would be square root of 4 or 2. Okay. So when I plot this, and what does this graph look like? Well, it's going to look like this. Okay. Now, this is a curve of the square root. The square root only exists for positive numbers. So what is the domain then? Well, it looks like the domain here, because we cannot go negative, okay? We cannot go negative. So this part of the number line for x we can't use. And so we would say that the domain for this is, for this particular function, the domain is a couple ways we could say it: x greater than or equal to 0, because we can have a square root of 0. Or we could say that it is all real numbers greater than 0. Or we could use our interval notation and say it starts at 0 with a hard bracket here, because 0 is included, and infinity this way with the soft parentheses to indicate, of course, that we cannot reach infinity. So there's three different ways that we can list the domain for x, okay? And again, a domain refers to the x. Now what about the range, okay, the y values. Well, where does the y value start? Well, the y value also starts at 0 because we chose not to include negative square roots. Okay, so for the range, and I'll write this over here, have been, again, for y values greater than or equal to 0. We could also have all real numbers greater than 0. Or we could have the interval notation. We do include 0 here, so it would be 0, comma, infinity. Now, the y values are not going to get there as fast as the x values. We can tell that by the shape of the curve. It sort of starts to flatten out, but nevertheless, as x continues to go out in this direction, it can go as far as it wants to if our graph paper was big enough, right? And the y values, although they're going to climb slower than the x values, they're also going to continue up this way until it actually tries to reach infinity. Of course, obviously never gets there because you can always have infinity plus 1. So that is a case where and again, this is it's restricted by the real number system, okay? Because we can only have the square root of a positive number, and we can only have, in this case, positive square roots. Now, I'll just mention while we're on this page, is that if we had, let's suppose this equation had been y equals plus or minus the square root of x, right? Then what we would have had a mirror image curve that goes this way, right? And we could have said then that the range would have been all real numbers, okay? But let's stay where we were. Okay, let's look at another example of domain and range using a quadratic equation. Okay, so let's look at an equation like, well, it doesn't matter what the equation is, but this is a quadratic equation. It's an x squared curve. Y equals something x squared plus would be ax squared plus bx plus c. And let's suppose that our axis of symmetry is here, and our vertex is here, and our equation is going to look something like this. Okay, now what's going on here? Okay, we've got little arrows here which indicates that the graph keeps on going, right? All right, let's look at the domain of this function. The domain, x values, x plus, x going minus, y going plus, y going minus. Okay, now first question, look at the graph. Is there any reason that if our graph paper were big enough, we could continue as far into the x plus direction or the x minus direction as we want, right? Well, it would take a really, really, really big piece of graph paper because the y values in this case are growing fast, but there's no reason to restrict x and y, right? Or x in this case. Let's talk about x first. So the domain then, again, for this one is x greater than negative infinity and less than positive infinity, or we could say that it is all real numbers, or we could say, again, that in interval notation it is from minus infinity to infinity, okay? So that's our domain. No restriction here, okay? We have not purposely restricted it in some way, so all the naturally occurring in the real number system is just from negative infinity to positive. Now let's look at the range and see what's going on with that, okay? Is there any restriction on the range going in the positive y direction? Well, there is not, okay, because as far as we keep going in the left and right, the y graph would continue to go up. And this is because it's a square curve, And on the x side, when we square a negative number here on the x side of, or the negative x side of the graph, the positive x will continue to go, right? Positive x squared, and so the y continues to go positive. So there's no restriction going y in the positive direction. What about in the negative? Well, no matter what we do and no matter what value we pick to plug in for x, guess what? We're not going below this point right here on y, okay? So the y value is limited here to the value of -2 on the graph. Here's 0, -2, -4, right? So the graph is limited by not going below -2. So in this case, the range, even though it's unrestricted in the domain, is restricted by the equation, by the limits of the equation in the range. And we would say that y has to be greater than or equal to -2, okay? And in the case of how we would do it verbally, we could say that it's all real numbers greater than or equal to 2. We could write that out in words. And in interval notation, we would say that, whoops, let me back up just a second there. We would say, because the value of -2 is included, we would have a hard bracket at -2, and we would say we're actually heading for infinity in the positive y direction, and that would be 3 different ways to list the range for that equation. Okay, let's take one more quick case where the domain and range are defined, okay? And so let's, for example, let's look at a case where we have looked at population growth. Let me create a new page here by cloning this, and then we'll erase it and start with something. Let's suppose that we are tracking the population of a city, okay? And we're going to say we're going to track population. Let's suppose we've actually written a curve that has population data since 1990, for example. Okay, so x would represent the years. We would define this as years since 1990, and we would say the population, by the way, y, or f of x, f of 0 is equal to, say, 1 million people. Let's start out at 1 million, okay, which we could abbreviate as 1 million, right? So 1 million at year 0, but year 0 is really 1990, okay? But the data we've collected is that, and let's suppose that that population curve does that. And so at 1 million, let's say this is 1 million population, 2 million, 3 million, and this is years since 1990, and we started with data in 1990, and say, let's say here's 1995. Well, actually, it's going to be 5 years since 1990, so we just go ahead and list it as 5. Makes it a lot simpler to graph this way. 5 years, 10 years, 15 years, 20 years, and so forth. Okay, and so 20 years past 1990 would be 2010, and so forth. All right, so let's and suppose this is our plot. So we start here at 1 million people, and let's suppose this population, somebody has actually plotted this population, and they've turned it into an equation, right? And so let's suppose we have, we would change this into an equation of f of x equals, and let's say it's 0.3x plus the population in 1990 would be 1 million people, okay? And so let's say that the population growth is doing this, and it keeps on, as far as we know, the population is going to keep on growing, so we would do that. All right, now what am I illustrating here? What I'm illustrating is here we are, not artificially, but we are purposely restricting the domain on this equation. We're not letting it go back here, okay, because we don't need it, okay? So as a practical matter, we can restrict the domain to start at year 0, and so we would say D domain is x greater than or equal to 0, and we could do this, the other ways to do it too. X starts in year 0. X is greater than or equal to 0. And of course the interval notation would be 0. And now would we go to infinity? Probably not, okay? What we would do is we would say, you know what? This model that we've created, this model right here, this equation, which we call a model, to model population growth, this model is probably not valid for more than, say, 10, 15, 25, maybe 30 years out. Who knows? All kinds of things change in the economy that would affect that. But we would say the model's probably only good for 30 years, right? And so we would say, let's cut it off at 30, okay? Now the data we would have plotted would have taken us out somewhere in here, but we created an equation to model the data. That's why it is continuous, okay? So this gives us, we took discrete data and we actually created continuous because we wrote an equation. And we'll learn how to do that in Algebra 2. We'll use a TI calculator to create a best fit line for discrete data, turning it into an equation. So, okay. So we've taken discrete data, made it into a continuous equation, and we would say, okay, let's cut it off here, okay? Let's forget about this right now, and we'll cut it off there. So we would say that our domain is going to be from 0 to, say, 30, okay? Where the 30 is years since 1990, okay? Now, what would our range be then? In this case, the range of this equation, we started at 1, right? And so we could say 1, and we could say, okay, what do you think this is going to be in 30 years? Well, in 30 years, the way we plotted our data, we may have plotted it to get this equation. It looks like in 30 years, the maximum population may be about 2.5 million. So we could say, okay, 2.5 or 3 million, somewhere out here. We don't think it's going to go further than that, so 2.5 would be the range for this equation based on the data that we have, okay? And so that is a case of a domain and range which are restricted or defined by what you might say common sense or practicality, all right? So that's domain and range. I would encourage you to look back over that a couple of times, and of course there will be some worksheets for you to look at and work out some examples. Okay, so that concludes part B of domain and range.